All right, so let's now talk about something actually very important. Okay, so from Tuesday's class, we talk about syllabus and also the open letter. So please take a look. We didn't really go over every single point in those two documents, but please read them through. They really set out the good standard and also expectation, for the coming 12 weeks. Okay. And today, the notes template is already there. You can download it for your note taking. This is somehow unpleasant. I was just notified by the department. Somehow the registrar office decided without our permission to switch the classroom. Okay, so I haven't been notified about the final decision. In the worst case, we have to go to 2 different classrooms on Tuesday and Thursday, but not here. Somehow this one will be taken from us. So guys, I'm just still waiting for the final confirmation from the registrar from the departments. I should know about the final answer later today or tomorrow. I will let you know by e-class announcement. But next Tuesday, for sure, you're not coming to here. There's going to be another classroom. Okay, I'll keep you notified. All right. Okay. Again, it's not our fault. Somehow registrar office decided that, right? It is actually a nice classroom. Somehow we have to leave. Okay. All right, so I think today I'll just continue since we didn't talk about anything very technical. So today the plan, okay, let me tell you the plan. So for the first half, maybe about hopefully no more than 30 minutes, I want to just go over with you maybe 1 or 2 motivating problems about the kind of problem we can solve by learning the materials until the end. And then in the second half, after taking a break, I would like to talk you through about some very basics about recursion, which is something I assume you guys already know from 2030. I'll tell you exactly the standard you're supposed to start with for this course. And then I will also start with a more challenging problem, which you can take as more like an expectation after the reading week when you take the first programming test, right? Well, I will talk about that example in detail next Tuesday. And then I will also give you the more advanced version of the same example for you to try it out as well. And then you should be ready for assignment number 1, right? That's kind of the plan. You definitely will get enough resources to get ready, but you just have to make sure you spend the time, not in the last minutes. All right. So the motivating problem, the first one we spoke about is so-called the searching problem, right? We talk about this one here. Basically, we got a very huge number of records in the database that we want to search, right? So that's something we said last time, okay? So let's go back to this diagram here. That's how we left off, right, from Tuesday. Okay, let's take a look at this one very quickly. So you got a linear or like a sequence of records over here, like an array, from index 0 all the way to 10 million records. So 10 to the 7 minus 1. That's all good. So now, the question is, if we have this, always when you want to analyze for how efficient a method or algorithm is, you have to worry about what's the worst case running time. Okay, worst case. Intuitively, worst case, what can be the maximum number of iterations in this example that we have to run to find out the citizen, right? So you can see that in this code over here, we simply got a for loop going from the first index all the way to the last index, right? And then every time inside there, we got to check to see where at index I, is it matching the SIM card that we're looking for? If it is, we're done. Of course, we might be very lucky. If the SIM card here we're looking for happen to be here, or happen to be very front of the array, that's very efficient. But that's not the kind of the case you can assume always. You cannot generalize it as a general running time for the algorithm. So now, what will be the worst case running time accordingly then? 10 million, exactly, right? Well, maybe very close to 10 million. That's something I'll elaborate a little bit more mathematically. So your fellow student was right. The worst case will be when you somehow you run a loop and you got to go all the way to the very end of the array. Well, let's say if the record simply doesn't exist. In that case, you will check everything here and then find out you just return false or return null, right? So worst case, let's document it, and then I will give you a little bit look ahead about what you will eventually learn to deal with this problem efficiently, okay? So the worst case. Oh, sorry about that. Worst case. So the worst case over here will be 10 to the power of 7, 10 million iterations. This particular searching mechanism is what we call a linear search. Okay, the term linear over here, and that's something I'll just mention that, but we're going to review that as well. The asymptotic analysis is simply something called big O of n, and n here is linear. All right, just for now, just note it down, okay? And then we'll talk about it a little bit more later. This is definitely not good because if you got 10 million, what about you got 100 million, right? Etc. So the number of iterations in the worst case will always be so proportional to the size of the database. We don't want that. All right. Let me sketch out very quickly about the solution you will ultimately learn by the end of this course. Okay. It's actually quite cool, even intuitively. All right. So this is something I'd like to sketch just a little bit. Okay. So let's now talk about an efficient solution. Efficient solution for searching. In a single turn, you have to build a so-called balanced binary search tree. That's what you have to build. Balanced binary search trees. So that will be the ultimate solution. However, in order to build this, it will take us about 5 weeks or so to really build out all the idea around it before you can actually see the exact practical, like a Java implementation, also theoretical underpinning, right? So you will have to understand what a tree is, and then you have to understand about what a binary tree is. And then you got to understand about what does it really mean when a tree can be suitable for searching purpose. And then finally, the most important one is about what does it really mean when a binary search tree is actually balanced. So these are all the various concepts you have to learn as well. That's something we'll guide you through, don't worry, at some point. But visually speaking, the database we're going to build is not going to be linear like this. You can see linear is, I got this one here, I got successor, I got successor, I got something after that, exactly what, right? It's like a linear structure. It can be a list, can be an array, can be a sequence. The tree structure here is something called nonlinear, a little bit like this, conceptually, okay? So we're going to start with some node or record that's called a root. And then, in this case, it can branch out rather than to just 2. It can branch out to 2 nodes right here. You can think about so far we got 3 records already, right? And then this one here can also branch out up to 2. And this one can also branch out up to 2 as well, and so on. Right? So that's kind of the structure we have to see exactly how to analyze its behavior. It's not just about coding, actually. Coding is definitely one important part. But another part is, how can you predict about how many nodes you might have at each level? That's something we'll see, okay? Definitely we have to review certain math for you to get this part, right? But conceptually, you can think about it's a big, giant tree right here. And then this part here, okay, this part here, is so-called the heights of the tree. And usually we just use a letter H. Why is the height so important? Whenever, just keep that in mind as well, maybe for the final exam. Whenever you're building a tree, always the height is the most important measure to know how efficient certain operation or like searching will actually take. Right? Let me draw another tree just to show you one more. Okay? Let's say this is the tree I have to start with. Okay, let's say this is the root. Of course, in real life, the tree will actually grow bottom up. But now in computer science or software engineering, it's going to grow upside down, right? Just the way it is. Okay. So let's say we're looking for maybe some SIM card number. And then we check to see whether it is equal to the SIM card number on the root. If it is not, we're going to go down 1 level. However, the way we're going to do the search in the tree is going to be a little bit different. Okay? But let me draw that abstractly. Rather than searching, for example, the next 2, and then search for everything right here, it's not the way to go, right? So all we do is, every time you search, you can decide, should I go to the left, or should I go to the right, and etc. So every time at each level, you only have to look at only 1 node. But why is it so safe for you to only look at 1 node without worrying about, I may have missed something? That's something we have to go over. There's some mathematical reasoning behind that, but just take it for granted for now. So if I want to search for that particular SIM card number, so I can just go left, right, conceptually like that, all the way, in the worst case, to the bottom of the tree, right? So rather than looking for everything in the worst case, all you got to do is go down in a so-called search path. So this is called a search path. The running time, like how efficient the algorithm is, depends on how long the search path is. And this search path will simply correspond to about how high the tree is. All right? So far so good, just intuition. All right? And now here comes the most important conclusion. Given that the tree is balanced, mathematically guaranteed, the height is about the log base 2 of n. N is about how many records you have in the database. In this case, 10 million. All right? Okay, I'll write it down. N here is about the size of the database. And let me just write a little bit equation for you. We used to have 10 to the power of 7 iterations in the linear search. But now, if we do balanced binary search tree, the running time will only correspond to how high the balanced tree is. In that case, we'll simply take log 2. All right? And I'll just write down the rough number just for your information. That one there is about 23.3, roughly. So up to 24. So now, let's compare. In the case of linear search, maybe this is something you have learned up to 2030. That's certainly fair. It's going to take up to 1 million iterations for very large database. However, after this course, until the end, you're going to learn that you only need about 20 up to 24, or log n in general, iterations to finish. Okay? Hopefully the big picture is kind of clear. Okay? That's something you can definitely look forward to. I would say that's one of the most important learning outcomes for this course that we're going to guide you through, okay, at some point. Okay. All right, that one's good. And then if we go back here, you can also look at the slides as well. Okay. Yeah, this one here, just another kind of motivating problem here. Okay, okay, this one, I don't have any iPad. Okay, just this. Yeah, this is just another one, but this one here is more about building some graph. It's more like an extension to trees. But in this course, 2101, we don't really do graphs. That would be like a subject to be heavily covered in 3101. So that's something you can also think about in perspective. At some point, you're going to build something more than a tree. You're going to build a graph. But that one there, I wouldn't worry too much for now. And graph is actually very useful. Let's say for the GPS you're using, if you're driving using Google Map, they are definitely using a graph algorithm behind the scene to really see what will be the shortest path for you to go, maybe travel from campus back home, right? In that case, they can also take into consideration about the live traffic data. So it's kind of the algorithm you will kind of learn in 3101, okay? But I wouldn't spend too much time on that for now. It's not a focus for this course. All right, one more. So this one here is kind of interesting, right? So this is normally the advice I will give to my students around the end of 2101, because the most important data structure to learn in this course is about trees. And there is a technology called compiler. You may have heard about the term before. Okay, if no, that's okay. So this is something I want to give you very quick, just about 5 minutes. Okay. So compiler is basically a program you can write. So compiler is basically just a program that can turning or transforming one thing. Oh, okay, good. Into another. Okay, hopefully that's stable. If not, I'm gonna reconnect. Oh, sorry. It's going to turn from one thing into another. A very typical example, like a very modern example is, did you guys take a database course before? Or maybe you would be taking it, right? You know, SQL, for example, this database queries, right? You can somehow use a compiler to really build a translator, maybe from Java-like. Okay, for example, you can see you got class, and also you got attributes, and also you got methods, right? So these are the OOP kind of stuff. Oh, it's not there, right? Okay. So over here, for this Java code here, good. Yeah, you got class, you got attributes, and you got methods. eventually the compiler can somehow turn this Java-like program with multiple classes into, over here, a SQL database with table and also different keys and etc. Right? Exactly how to do it, of course, it will be hard for you to imagine. There will be many things behind the scene. But in the general idea, there is a program technology called compiler. And the compiler can turn one thing into another. And one example would be turn Java-like program into SQL database. Okay? And behind the scene, okay, let's see a little bit more. Just see another example. Behind the scenes is all about tree recursion, which is what we're going to learn in this course. Okay? So at the end of the course, when we wrap up the course in the final lecture, I'm going to give you guys some reference. Maybe for the summer, if you're interested in doing some side projects, one recommendation would be try to build a small compiler yourself. It's going to be a very nice way to maybe sharpen your CV a little bit. Anyway, I can talk to you a little bit more about it. But just see one more example, and then we're good. Okay, let's look at this example program here. Okay, it's not exactly Java syntax, but let's explain that. We got three variables, A, B, and C. And then across here, it's just like a domain-specific language syntax. It's like a for loop. The loop counter is I, and then I will go from 1 to n. You can think about n could be the size of an array, right? Could be any number that's already set. For every iteration, first of all, we're going to read into variable d some external input from the user. Okay, standard, for example, standard input from the keyboard. And then for every iteration, we're going to update the value for a by this expression. Right? So that's what this program will do, a piece of code right here. Okay? A typical compiler's job will be to optimize the code that you are supplying. For example, if you're taking 2031, the C code you're learning, when you say compiling the C program, that one there is also going to do stuff along this line to optimize the C code and then turn that into machine executable code. Right? Similar. But just for this one, for example, can you see any kind of inefficiency for this program? And if so, how would you improve it? Inefficiency in the sense that there might be certain tasks, you keep doing it for each iteration, but you really don't have to. Maybe do it once will be enough. That'll be a little hint for you. Okay, go ahead, please. Okay, so let me just be more precise about what you're saying. Are you suggesting about which part? This part here? Or you're talking about different part? Around this line, right? Yeah. 2, B, and C. Okay. You're saying this part here is somehow not efficient. How come? Remain unchanged, right? Somehow, right? So it seems like we have to evaluate this value here for every iteration, but the value will just be the same anyway. Why should we evaluate? Let's say if the loop is going to run 1 million times, we've got to evaluate the same value 1 million times. So it's a waste of resources, right? Along that line. Good? Okay. So for this one here, let's isolate it. This part of the expression over here actually stay unchanged between iterations. So there's no need to really do it for every iteration. So the compiler is going to identify this particular pattern of inefficiency, and then it's going to automatically rewrite the program using the same syntax. So you can somehow expect the output for the compiler is going to look like something like this. Whenever a compiler tries to do any optimization, etc., it is not going to change the external behavior of the program, meaning that whatever that used to achieve by the program is still going to achieve the same thing, right? So now in this case, you can see this expression here, 2 times B times C, is now only evaluated once before the loop, and then it's stored in this particular variable right here, right? Only once. And then we're only referring to this particular value for every iteration. There's only one computation, and it's all about reading afterwards. Right? So like one kind of a optimization, just for you to see the idea. One more detail. How exactly is this one done? Right? Let's get a little bit more detail for you. Okay. So if you're the software engineer to really implement this compiler, right? Number one, you will have to somehow design the syntax for this particular language. Number one, for this language here, you have to design the syntax. This is only for your information. There's something called context-free grammar whenever you want to design languages. That's something you can definitely look into if you're interested later. It's not part of the course, okay? And then we're somehow going to turn this program over here into a tree. A little bit like a binary tree that we spoke about earlier, but it's not exactly binary tree, but it's a tree, okay? And this so-called parsing process over here is going to be not manual. It's going to be automated. And out there in the market, there are many compiler tools that can help you do that. And you can choose to either implement your compiler using Java, Python, C, or C++. C used to be the very first language for compiler, right? And at the end of the course, I'm going to suggest to you guys, if you're so comfortable with Java, Antler 4 is one tool actually for you to implement such compiler. And once you understand about the idea about compiler, it's very powerful. You don't really have to just translating from programming language to programming language. It could be from natural language into a certain prompt that you want to fit into some generative AI tool, for example, right? You can just be very creative about how to use a compiler, right? All right, so this part here is just about the tree. So this is a tree, or abstract syntax tree. That's the formal term, but you don't need to worry. I'll just mention that. And this course here is going to help you gain the foundation for compiler. When you go from one tree that corresponding to the non-optimized program, eventually you want to turn that into the optimized version. This transformation over here is going to involve lots of recursion. So that's why we have to emphasize recursion as well, right? Mostly recursion. All right, anyway, so that's the big picture about compiler, right? So it's only for your information about this, such a very big thing you can actually really do at the end of this course. You can definitely put that into perspective, okay? If you're interested in talking about just compiler in general, feel free to drop by office hour. More than happy to talk more about it, okay? I do have some knowledge about compiler, okay? Okay, so that's about the motivating problem, okay? So let me just do a little bit, guys, any questions? Basically, we're done with the introduction part for the course, right? We see some code of ethics, and also about data structure, algorithm, some definition last time. And then we have seen some motivating problems. It's now really just good to go directly to the course. All right? Question, please.
Why do we need read D? Isn't that redundant too because it can just be I?
Good question. Okay, I see exactly what you mean. Yeah, more talking about the D over here, right? So the D here is not necessarily just a value for which iteration you are. For example, I here is going to be 1, 2, 3, 4, and up to, for example, 1 million, right? Let's say in the 5th iteration, I value will be 5. But now the user may enter something other than 5. So D here is just any arbitrary number the user can enter. Yeah. Well, D may just be a string rather than just numbers, right? So just arbitrary. Good. 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 Okay, let me go a little bit, like a 15 minutes or so, and then we'll take a short break, okay? Okay, so just to remind you guys very quickly, so the slides that I'm going to talk about today is also on the lecture site. It's recursion part 1, okay? So part 1 is only mainly about giving you the necessary resources for you to pick up the basics. If you don't really exactly feel comfortable, you definitely get time to really catch up before assignment 1 is released a little bit later. And then I'm also going to go over some exercises with you and then assign some more advanced for you to think about before we actually solve it together. So for next Tuesday, I will highly recommend, for those of you who usually don't like a laptop, you can bring your laptop actually, because I'm going to do some Eclipse debugger together with you. I think that's going to be a very worth exercise we can do together. That might be the only time I can do that in a class, right? Okay. So that's the slides. I'll talk about these resources a little bit later. Okay, let's just go to the slides. Okay, we'll go for 10 minutes and then we'll take a break. All right. So coding bet. Okay. So here's the deal. Okay, I would suggest you can plan your time. I would say in the very first 2 weeks or so, just for basics, try the coding bet problem recursion 1. I think those are the ones that's kind of more basic, only about how to do some simple recursion on the array. Okay, I'll show you. If you click on the link, you may have seen this similar site before, not necessarily coding bad, right? So they got tons of good exercises for you to try, right? So if you try any one of them, for example, go to count A, for example, they will give you some informal description over here and give you some input-output specification. You can think about this will be more or less the format for your programming test 1 and 2, more or less, okay, similar. But I'll try to make the description in the programming test a little bit more descriptive, right? Sometimes it could be oversimplified, okay? And then you can actually do your coding right here. I would say if you do the coding directly on the web interface, the disadvantage is you don't see like a live feedback from like an Eclipse to tell you may have some compilation error. So if you really want to take it more seriously, I would suggest for every, just make it systematic for you, right? You can open up, launch a new project for yourself, and then for every problem you're trying to solve, make a new class, or new file, and then make a new method. And then time yourself. Maybe for coding bad, problem category number 1, I would say take no more than 20 minutes for each one. If you're able to solve much faster, that's great. But you gotta train yourself, right? Always when you do exercise, time, right? Don't really give yourself like a 1 day to solve only one problem. That'll be too generous on yourself, right? You want to give yourself a little bit of pressure, healthy pressure. Okay, so that's about coding bad. And then if you go back here, so that's about coding bad number 1. Okay, that's the 1. And then recursion 2. Recursion 2 is going to be more similar to your programming test number 1. All right, so I would say get the basics caught up first and reach out to me if you got any trouble, and then try it out recursion 2. What if you finish every one of them? Great, very good. Then you may want to maybe Google a little bit just to see if there's any online resources about this kind of problem. Maybe LeetCode, I believe they got many free exercises as well. You don't really have to subscribe, or you can go to any other interview website. Okay, you can take your pick. Okay, the resource is really there. And then, okay, so this one I'll mention. So beyond this course, if you really want to be very good in recursion, compiler is one thing, and then, or learn something called functional programming language. So for those of you who are kind of very interested in math or like a linear algebra, that kind of stuff, functional programming language might be something you like even more than Java, right? That's only for extra practice, okay? For this course, worry about these two, okay? And then, okay, basic recursion. So this is for the background study, okay? So something I assume from 2030, either maybe you took 2030 with me, or maybe you took it with other professor, doesn't matter. You know, I would say, just to be sure, these are the very basic questions. You know, things like what does it really mean when the method is recursive, and what is really a call stack? How do you use a call stack to trace recursive call? For the more advanced example I'm going to do on next Tuesday, I will show you the call stack. Maybe not today, okay? And also, how do you use recursive helper method as well? That's something you will have to do as well for the programming test later, okay? So these are some parts of the lecture if you don't feel comfortable about recursion. So these are the stuff you can actually do as well. So I would say for this slide here about the basics, try to use the beginning 2 to 3 weeks to gradually catch up, right, about the basics. The Tower of Hanoi is a very good one, a little bit slightly more advanced recursion on the array. Okay, it's good practice for you as well. So the best thing for you to do, start with the slides over here. Just skim through them to see if you feel comfortable about the ideas mentioned there. Any part is not exactly comfortable for you, maybe you want to study that part, right? So I'll leave the choice to you. Okay. And there's also some recursion labs from the older version, like an older semester for 2030. You can feel free to practice them too. And the solutions here, right? Everything's there. Okay, and feel free to ask me questions about recursion, okay? So far, I haven't really been confirmed about the TA for this course. I think if you got any question about the course in general, assignments, theoretical stuff, programming, just drop by office hour, right? You can just come by, okay? But if we really got lots of demand for help, I can possibly schedule some TA hours, you know, maybe Zoom or maybe in person, so you guys can still talk to the TA, but we'll see. All right, so this slide here, please just make sure, basic. That's something I have to assume. okay, for this course. But I do want to revisit some very basic principle about recursion. But let's do that today, right? We do have the luxury of time just for today. So recursion basics, what we'll do today. And then resources, I just mentioned that in the previous slides. And also the more advanced recursion. So for today, at the end, I'm going to mention that problem about recursion, more advanced. You can give it a try, or at least try to sketch some idea. And then for next Tuesday, we'll solve it together completely. Okay. Recursion principle. Okay. Basically, recursion is a method calling itself, basically, right? There are base cases, and there are also recursive cases. Okay. And you can read through these bullet points over here. I'm going to visualize it a little bit for you. But it's actually nice at this point to make a little bit connection from recursion to mathematical induction. I'm pretty sure you have seen that before. But maybe you never try to connect these two ideas together. They are very similar in some way. Okay, let's try to do a little bit of visualization here. Okay, right here. Okay, how do you really solve a problem recursively? Okay, let's see. Okay, that's okay. Yeah, in case you see me writing but it's not really showing, please let me know. Seems to be fine. Okay. So this principle here is not going to apply just to the basic recursion problem. For any recursion problem, doesn't matter how advanced it might be. Similar principle, always the same. Okay, let's see. Good. Okay. So let's see very quickly about mathematical induction. Okay, I'll just draw that aside. When we talk about mathematical induction, specifically, we're talking more about strong mathematical induction. But in this course, you don't really have to distinguish between weak and strong mathematical induction. You don't have to. Right? I'm just going to write it out directly. Okay. So let's say the idea is you want to prove. I got to be more careful. Okay, sorry about that. Guys, I'll promise. Okay, so let's say our idea about this one here is to prove something. Okay, let's say I want to prove a certain property that will hold for any arbitrary value of n, and maybe from 0 all the way towards infinity, right? N is just like a number, right? We can think about n here could be maybe a certain array. You want to prove something inductively about an array. Go from index 0 all the way to, doesn't matter how long the array is. That would be one analogy, okay? So what do you do usually for mathematical induction? Just abstractly, okay? First of all, you have to prove base cases. You have to prove about the property will hold for maybe 0, you will hold for 1, maybe you will hold for 2. And typically, you don't really have to do that many base cases, just 1 or 2 or maximum 3 around that line. Okay, so that would be the base case proof. And then we somehow have to make some inductive hypothesis, assume something is going to work. Okay, and then we're going to assume. For example, we say P here, it could be K minus 1 and also K minus 2, etc. You can assume for as many as you like. Think about the assumption you're making over here is about how many recursive calls you're making. All right, I'll connect to it a little bit later. Okay, so about making assumption, and then you will have to somehow do some manipulation to show that P of K is going to work. And then you actually show that P of K is actually going to work, and then improve everything, right? So that's roughly the steps you will do for mathematical induction. There's going to be only one example for math induction we'll do at the end, around when we talk about the trees, after the reading week. But at that point, we can see even more about mathematical induction. What about recursion? That's what you have to worry about, okay? So let's say we have a problem. Depending on the size, if the problem size, like the array, if the input array is very small, that's basic case, right? So if this problem is very small, you can solve it right away, okay? So the blue one here is about problem, and the green one here is about solution, just a convention, okay? So this one here will be the base cases you have to define. Base case. for your recursion. And typically, base cases should be rather easy, okay? In practice, I think some people like to program the base cases first, just to get something done. And some people like to worry about the recursive cases first. I would say you can choose either, whatever that seems more intuitive to you. You don't want to fix yourself to only one pattern, okay? Let's say the problem itself might be too big for you to solve right away. So here comes something similar to mathematical induction. So you're given something so big, and then you got to do something called divide and concur. Okay, I'll write down the term for you as well. It's called divide and concur. Okay, we're going to divide the original big problem here into smaller subproblems. And for each smaller subproblem over here, we assume there is a corresponding solution. So the assume part is really important, right? That's something usually you will find a little bit not very intuitive, especially when you're doing recursion. That's something I will show you as well on next Tuesday. All right, so this part here is very critical, okay? And for this part here, I'm going to write it aside, okay? For each subproblem, assume that a solution exists by making a recursive call. I will try to revisit this particular principle maybe next time when we see the concrete example. But for now, you can just take it down. Right? It's also very important insight about recursive method design. Okay? For each subproblem, assume there's a solution exists by making recursive call. Okay? So now we got solution for this problem here. We got solution for this problem here. We got another solution for this problem here. The final step is for you to actually combine all these sub-problem solution into a bigger one. And this big solution here is going to be the ultimate solution for that big problem that we couldn't solve in the first place. Okay? Feel free to check out the recording just for this part here. This principle here is going to apply to every recursive problem you're going to encounter into for this semester. Simple principle, but it's very powerful. Right? You just need to do lots of exercises to see exactly how you can adapt it to different problems. Right? So this part here, give me one more turn. So this will just be a combination of solutions to subproblems. Okay, and this fragment of code is simply say whenever you have a method here and you're calling itself, is a recursive call. Right? And another very important principle is whenever you're making a method call, like a recursive method call, so here the input to recursive call must be strictly smaller. Okay, strictly smaller cannot be the same, but must be strictly smaller. So in this case, when you actually look at the j here and I here, right? J here must be strictly less than I. Okay. Also, that's another principle which I'll try to recall as well when I get to the concrete problem next Tuesday. Any questions about principle here? Okay, you guys deserve a break. Okay, I would suggest we pause the recording. All right, so there are three more things I want to talk about today. I'm just going to switch to actually the iPad, but the slide is not very long. So you will see some definition for cost stack. So please look at the slide of your bullet point just to revisit about what cost stack is. If you really want to look at some little bit more detailed example, you can definitely look at Fibonacci sequence. I think it's a very nice example to actually see how the cost stack is going to work. So at the end of this particular slide, slide number 7, you will see there is a little video recording over there. It kind of shows to you how you can use a cost stack to trace the Fibonacci sequence recursively. Right? That's something I also recommend you to really make sure you are comfortable of doing that. That will be part of the basics, I have to assume. Right? And then, so this is something, okay, so now For the slides, you can just go all the way to about slide. Yeah, you can see now it's not very long, right? So I'm just going to switch to my iPad right now. Okay. So 3 things I want to talk about today, right? So you'll be pretty much ready to start your own study. Number 1, I want to revisit an idea called call by value from 2030. You may have heard of it, maybe. If you took 2030 with me, I'm pretty sure I have heard about it, but that's okay. If you forget, we'll review. Call by value is very important for recursion because every time you want to make a recursive call, you try to pass by the value of some collection. Could be an array, could be something else, right? We'll talk about it. The call by value, we'll do some example and some principle, and then the coding bet problem category number 1 is mostly about array. I just want to go over with you about some idea of how that particular pattern of problem should be understood. Not like a very concrete example, but if you go into the resources, you can definitely see some concrete example. But for this one here, just a quick review about the principle. And this one here is the more advanced example I want to solve together with you. So today, maybe around the last maybe 10 minutes or so, I'm just going to walk you through about the specification of the problem to see the input and output, do a little bit of visualization. And for those of you who just want to try to see how to make it work, you can go ahead and try. If you really have no clue, at least try to sketch some idea maybe on a piece of paper to see how far you can get to. And then on Tuesday, we solve it all together. Okay? So that'll be the 3 things I want to do in the second half. Let's start with the call by value. Okay? So it's something called call by value. Okay, it's a principle you will see in any object-oriented programming language, for example, C# or maybe any OOP, Java for sure. Okay. So let's now see the pattern first, and then we'll see one quick example. Okay. So let's say we have one method here called n, and n sits in class A. So we say that the combination of A, which is the context, and also n here. So this is a method that is supposed to be called by somewhere else, right? So this is what we call a callee. Okay? Some method to be called, to be used. On the other hand, this is one example place we are trying to call that particular method, so which we call the caller. Okay? Let's identify that. So you can see inside class B, and then inside method n. Inside this particular method here, we are trying to call that method. So this is called a caller. Okay? Caller versus callee. Every time you have a line of method call, you have the caller-callee relationship. Right? And we are having this particular one here, right? You can see this is the method call. And we know that the object to the left of the dot is called the context objects. And the context object CO is defined of class A. You can see A is right here. So that's why you can call method n right here. Right? You can see everything is kind of connected, right? The way you kind of learn from 2030. Nothing surprising. Right? So what's really call by value? Call by value is saying that, imagine that I use Eclipse to execute this method here line by line. Imagine. Okay? I can execute this line here, and then I'm going to pause right here, pause the execution. And then I can somehow step into the execution for this method. I'll show you how to use step into maybe on Tuesday as well, just to remind you. Okay? If you somehow step into the execution for this particular method, that means you're going to go into this method here, right? Because I'm calling n, so that means n should be called right here. Call by value tells you that there will be one line of variable assignment done implicitly as the first line. Okay? Let's see exactly what it is. So for that one there, I'm just going to link them. Okay, so whenever you're trying to make this method call here, so call by value tells you that this is a variable which is called like an input parameter for the method definition, right? The paren over here is going to assign the value of the input value here for the method call arguments. This is the call by value idea. Okay? In the case where the argument and the parameter are reference type, like objects, you're somehow sharing references with between the method call. And this is a very important insight when you're trying to do recursion. Okay? So let's get this principle done first. Okay? So all you need to pick up from this page over here before we do one example is whenever you have a method call, most likely the argument here might just be an object of certain type. There's a call by value principle, meaning that whenever you're trying to execute this particular method call, one line is going to be done before everything else, which is going to assign the argument value to the parameter. Once this assignment is done, we do the rest of the method. Okay, so that's the principle. I've got to do one example, okay, just to brush up. Okay, let's do one example together. Very simple one, okay. Let's say we have the class called circle and some attribute called radius. We got a constructor and we got another constructor which will take a radius and assign the radius value. And then we got set radius method which will change the, okay, so set radius is going to take a circle. Right? You can see the parameter over here, C, is of reference type. And then it's simply going to set the radius of the current objects to this input radius, this input circle's radius. Okay? And then we have some use over here. Right? That's roughly the sketch. But we'll trace the code together. Okay? So let's say we're going to execute this block of code, right? Again, let's recall. So circle user, and this will be where we are trying to call the method. And then, okay, just make sure. And this method here is the callee. Is some method that's going to be called. All right, just be clear. Okay, let's now trace the code, line by line. Line number 1. So we have a circle called C, and it's simply a new circle. So we are basically calling this constructor right here, and you will just set the radius to be default value 0. All right, so let's visualize it. So C here is a reference variable. It stores the reference of a circle object right here. Okay. So this will be type circle. Okay, and every circle has a radius. Okay, I'll just say R. And then this constructor here is like a default constructor, just do nothing. Okay, so it will just be value 0. Okay, this line here is just like that. Okay with that? Okay, and then the next line. The next line there, we're going to have another circle. And that circle there, we'll just call it arguments. Okay, so arc points to another circle object right here. You can see just another new keyword. And that one there is going to be circle. And then the value for the radius is going to be 10. All right, 2 circles so far. All right. And then what we're doing is we have a line of method call. And now if you analyze this line here, be very careful. We got 2 circle objects right now, right? You can see the C here is the context objects. The argument here is the argument being passed for the method call. So they have different roles, all right? And since we have a method call, so call by value is going to have some impact before anything else is going to happen. Okay, let's now map it out. So think about we got circle C parameter, and also we got this particular arguments, right? So now let's see what the call by value is going to do for us. So think about, okay, I have some connection between these two, caller and callee. The call by value is going to have parameter C is actually going to be equal to the arguments. Okay. However, this example here, notice one thing here. That could be deliberate. You got to be careful. Okay. The C over here is the local variable inside this class. The C over here is the parameter name, even though they're called C, but they're not really the same C. They belong to different scope. Behind the scene, Java will be able to tell the difference. You shouldn't really mix them as the same variable. That's my point, okay? So I think in some of this example is nice. Of course, I could have chosen different names, okay? But you just gotta watch out for that, okay? So I'm just gonna use this color here, okay? So this C here is the parameter, right? It's going to be the C. So that means I have another C right here. So that's a parameter, okay? So this is the parameter. And the call by value is saying that C is now going to be assigned a value of arguments. Okay? What does that mean? That means, okay, let me just move the C to here. I think that'll be better. Okay, C is a parameter. It's now going to point to wherever argument is pointing to. Okay? So if you recall what you learned back in 2030, if you are doing assignments for reference type, so that means C will store the address of arguments. So diagrammatically, C is now going to point to wherever argument is pointing to. All right? If you're really having trouble about this kind of reasoning or tracing, yeah, we'll take question first. Yeah.
When you say C dot set radius, like that C is the object you created above?
Yes, exactly. You can think about the C here is like a blue one. It belongs to a different scope. Okay? You can think about the C here. That's a good question here. Let's be careful. So now call by value is done. Okay, let's now try to trace the code one more line. Let's see how that one should be understood. So now we're actually going to do right here. This line. All right, let's now put everything together. The context over here, let's first of all, what's really this? This corresponds to the context object for this method call. Since the method call we are talking about is the C over here. So that means that this here is really the C, which is right here. All right? And we are saying C dot radius is going to be C dot radius. And what's the green? Green C dot radius. So C dot radius will be 10. So we're going to update this value here to be 10. That's what we're doing. All right? Any questions? Any part you want me to repeat? Okay. So this kind of call by value is going to happen all the time whenever you want to make a recursive call, right? I'll give you guys maybe some practical tip about how you're supposed to think about call by value when we get to the debugging on Tuesday. Okay? So make sure before Tuesday, feel comfortable about the basic idea about call by value, right? It's very, very crucial. Okay? All right, first thing done, call by value. And then second thing, okay? So one very quick reminder about the coding bat, category number 1, right? About how you can do recursion on the array. Okay? We can apply call by value right away, okay? It's actually related, okay? So let's say this. So let's say you only want to run a recursion on the array, right here, okay? Let's say we have a method here called n. And then we have an input array A. Okay? However, this A here, the reference or address of A is somehow going to be passed around different recursive call. We'll see exactly how, but let's write it down. The array A here, the value of A's address will be passed around between recursive call. And we'll see exactly how. Just one moment. Okay? The value of A's address will be passed around between recursive call. Okay? You will see call by value. Okay? And then right here, we have one pair of integers called from and to. Okay? So these two integers, the purpose is we want to specify a range of the array A that we want to look at for the current recursive call. okay? Rather than creating another array from scratch, which is going to be very expensive space-wise and timing-wise. But I just want to pass the reference and tell you that at this particular recursive call, only look at these indices. Okay? That's conceptually the idea. Go write it down. Okay? It's actually specify the range of indices in A to look at in a specific recursive call. And by doing this, we don't really have to create any subarrays from scratch. So we are really saving time and space without having to creating new array objects. All right, so that's really why we're doing this. Right? So let's go directly to tracing to see what's going on here. Okay, there will be base cases you can think about. Let me just these two are the typical base cases. Okay, so these two are the base cases. But as we trace, we'll see. And this is, for now, the single recursive case. But in general, doesn't need to be just one. You can have as many recursive cases as you like. Okay, for now, just one, for simplicity. Okay. What does it really do? Okay, let's just trace two examples, and then you will see. Okay, example one. Okay, so let's say we have A1. So let's say we got A1 is empty array, right? So think about visually, it's not really null. So A1 is really pointing to something, but that array has no valid indices, like empty. It's still something there, but just no valid indices. So now we got A1, the reference. And then we say from, usually from should be like, for example, start from 0. 0 is always the leftmost index. We start with that. And now A1.length minus 1 should be the last index. So in the beginning, we say we want to go from the leftmost index to the rightmost index, right? A1.length, in this case, should be 0. So 0 minus 1, which should be minus 1, right? So now, if you look at that, 0 and also minus 1. So that's a from and to that we are doing. You will see that from is larger than 2. So this is the typical first base case you might run into. It's as if you're passing an empty array. We're passing A1, but tell you that it's empty range you have to look at. It's as if the input array is empty. Okay, just one base case. Okay, but let's see the recursive case in this one. Okay, let's see the recursive call that we're going to see. Okay, let's visualize that array right here. So let's first of all draw that. I got A2. A2 is pointing to the beginning of some array. You can see 0, 1, and 2, the indices. 0, 1, and 2. And we got A and B and C, right? That's the array. Typically, you would just say, I want to start my method or algorithm with the intention to look at the entire range of the array, from 0 all the way to 2, right? In this case, 0, 1, and 2. That's my intention. So when I make the method call, I'm going to say and pass the reference of A2 from index 0 to index 2. Okay, so you can think about this is the initial method call. Not the recursive call just yet, right? The initial one. Okay, so this one here will be the from and then the 2. All right, and if you look at the 0 and 2, you can see 0 larger than 2, false, right? And also 0 equals 2, also false. So it's not a base case. Go recursive case. What does a recursive case do? Recursive case saying that presumably for this particular method call, you would have already looked at maybe one element already of the array. So for the recursive call, you should really try to reduce the range to be something strictly smaller. Let's say I used to look at the entire array. But now, for the first recursive call, I only want to look at this sub-range instead. Right? That's just one pattern that's possible. Okay, let's try that. So the very first recursive call, so this will be the first recursive call. That one there is going to call n, and now you can see we are passing a2. So this is why I review call by value. Whenever you're making a recursive call, very rarely you have to reconstruct the array using a for loop, very rarely. Okay? So you simply just pass the reference. So think about this one here, it's really call by value. Call by value. And now, according to the recursive call, you're going to pass from plus 1 and then 2. All right? For the initial call, let me just highlight it quickly. Okay? For 0 and 2, that means I want to cover the entire array. But now, for the first recursive call, I'm going to pass from plus 1. So 0 plus 1 is going to be 1, and then 2 simply stay the same. Right? 1 and 2. So rather than passing a new array, I simply pass new indices. That's more efficient. Okay? 1 and 2. How does that represent visually? So it's going to be just 1 and 2. Meaning that I start with this particular range. In the first recursive call, I want to look at only this sub-range, and so on. Okay? So now for 1 and 2 over here, you can see 1 and 2. 1 larger than 2, false. Also 1 equals 2, also false. So another recursive call. So now I'm going to increment 1 just by another 1. All right? Let's do one more. So that one there is going to be a second recursive call. And again, call by value a2. And then I'm just going to 1 plus 1, 2, and then 2. So that would mean in the second recursive call, I only want to look at from 2 to 2. Right here. Okay? You can see the range is becoming smaller. Remember we said earlier in the principle, whenever you want to make a recursive call, make the input strictly smaller. That's exactly what we're doing here. All right? Just make the range smaller and smaller. Okay? Okay, so that will be this one here. And this one here. All right, so this is just a very quick mention about the principle on some simple recursion on the array. So the best way for you to practice is to look at a study resource, and you'll see lots of examples like this. All right, question? Okay. All right, one more. Okay, 10 minutes, one more. But just to be safe. All right, so that's about the basic for recursion. Let's now look at something more advanced. So this is something, as I said, will be closer to what you can expect about part of the programming test 1. But of course, I'll definitely give you enough resources. We'll cover enough as well in the class. Okay, this one here, I took it straight from Coding Bet category number 2. Okay, so you can feel free to go to the link if you really prefer to work on the web interface there. But again, I still recommend you to do that on Eclipse. I think that'll be better simulation for your later test. Okay. So now, can you guys, maybe as a practice, why don't you look at the description just for 1 minute? Okay, look at that. So try to look at the problem description over here, and then look at the input and output. How about 2 minutes? And then after the 2 minutes, we can discuss very generally about the idea to make sure you understand the problem, and then we are done for today. Okay, 2 minutes. Okay, just to understand what exactly is being asked. I'll make it a little bit bigger. As you can see, no loops needed, right? So that means this one will really force you to think about how you can do things recursively. Okay. Okay, take one more moment. At least everybody somehow getting some idea about what the problem is, right? We're not going to solve it right now. I just want to give you some visual intuition. I think that's more important before you get to solve the problem. Okay. All right, so this is a problem description. You can also revisit that. I'm not going to read it verbatim, right, since you already read it. Let's try to look at maybe this example over here, right? Just analyze them. In this case, it's going to be returning true or false. I would say, if you think about it, in some way, a method returning true or false, you can just guess the result, right? True or false. You got 50% chance to get it right. So typically in the programming test, you wouldn't see a method that's going to return true or false, right? Because I want to be fair to people who really know how to do things rather than just guessing, right? But it's okay. It's a first example. The more complicated version for this one here is going to require you to use some array list. That's something I'll assign to you and give you a solution, and also some solution walkthrough video. Okay, but let's focus on this. Example number 1. If the input array is simply 2 and 2, it's true because there's a way for me to split it. So you can think about over here, I can split this array, let's say G1 and G2, group number 1 and group number 2. So group number 1 is going to contain just 2. And also group number 2 is going to contain just 2. The sum of this array, 2. The sum of this array, 2. So 2 and 2. So true, as long as it's one way. Okay. How about this one here? Is there any way to split it? No, right? It's just false. Because, the group cannot be empty. That's all the part of the requirements. So the only way you can split is 2 and 3. They're not the same. And for this one here, as you can see, the way to split it will be, I can split that into maybe group number 1 is going to contain just 5. And group number 2 is going to contain 2 and 3. And the group don't necessarily have to be consecutive. For example, I'll give you one more. Okay, if I do, let's say, split array. Let's say here. Let's say 6, 9, and then 3. All right, for this one here, should it be true or false? True. Agree? All right, because this one here, by the way, this is not B, that's 6, right? Just in case you're wondering, okay? It should be true because I can put 6 and 3 and also 9 as a split. And at the same time, you can see that 6 and 3 are not consecutive in the input array. They don't have to be. So it might be more complicated than you might think. All right? Okay, that's a problem. All right? And this problem here is actually a very nice pattern for us to think about. For recursion, it's a very nice way for us to specify some very few lines of code. And then when things really happen at the runtime, it's actually going to somehow consider all the possible combinations of the input. That's insight I will also see on Tuesday. But let me just do a little bit of intuition with you. We're going to get about 4 minutes. I think that's good enough, right? So let's say this. So the intuition is going to come from your Math 2030 class about combinations, all right? Permutation and combination, that kind of stuff, right? But I'll write it out. So from your Math 2030, you're basically asking how many ways to put n elements into m groups. I'm pretty sure you have seen something like that, maybe back in 2030, when you have to calculate probability, etc., right? That's exactly what we're doing here. It's pretty cool, because to support this kind of recursive programming, you have to understand the math, okay? So in our case, let's say, just take this one for example, right? 5, 2, 3. We got only 2 groups, group 1 and group 2. So m here is simply just 2. And N here is about how many elements are you considering. We got 5, 2, and 3. So we got 3. So now, how many ways there are for us to put 3 elements into 2 groups? Right? Guys, that's okay, right? I know maybe you haven't seen that for a long time. No problem, right? How about multiple choice? Okay. In general, would that be n to the power of m, or should it be n to the power of n? Multiple choice. Only one correct answer. Anybody? The second one? Ah, sounds pretty good. Oh, you say, that's pretty true. Yeah, I agree. Yeah, awesome. Just in general, right? So here, I think for the math formula, you're right. In that way, since we don't, in math formula, it doesn't really say you cannot have empty group, right? But for this programming exercise, yes, I like that. Good. All right, so this one should be the way to go. Okay. So conceptually, how do you understand that? So basically, you got your n elements. 1, 2, 3, 4, all the way to here. So you got n elements. And then for each one of the element here, which group? It could be group number 1 all the way to group number n. Right? So for the first element, you got n possibility. Second element, you also got m possibility to put that into either of the m groups. Right? So that's going to multiply all the way to, so you got the products of n for n times. Right here. It's a very quick justification. All right. So now, how do we apply this to our problem here? All right. I got only about 1 minute, but I'll try my best. Okay. Let's try to visualize. In this case, how do we figure out? Okay. Okay, guys, give me about 2 minutes. Okay. Let's say this. Let's say we start with 2 empty groups, just for now. It's not valid, but start with that. Okay. Since we actually got 5, 2, and let's say let's make it even simpler. Let's say the input is simply just 2 and 3. Okay, even simpler. Okay, just 2. Okay. So now we got to handle one by one. When we look at the first element 2, we got 2 choices. Either 2 is put into group 1. 2 might be put into group number 2. So you got 2 parallel possibilities, right? So it's going to be either I got 2 over here, and second group is empty. Or I got empty first group, and then 2 over here. Follow? And based on each one of them, there will be another 2 possibility for the element that we're going to consider next. Okay, let's write it out. So for 3 over here, right? So now, based on this, we got 2 possibility. So 3 can be put into group 1. 3 can be put into group 2. Right here as well. 3 can be put into group 1, and 3 can be put into group 2. That means eventually you will get 4 possible splits, eventually, right? Let's write them up, and then we're done. So now for this one, 3 might be in group number 1, so that means we got 2 and 3, and leaving this empty. Of course, that should not be allowed, but just figure out the possibility first. And this one here, 3 will be put into group 2. So that means we got 2 and then 3, right? This one here in group 1, so 3 and then 2. And here we got empty group 1 and 2 and then 3. So you can think about somehow we got 1, 2, 3, and 4. 4 possible split. On paper, intuitively or mathematically, you shouldn't really have any trouble, right? But what we'll see that's really cool is somehow this kind of like a very exhaustive enumeration about all the combinations is going to be done based on how you actually specify the recursive call. That's something we'll see, and we'll dive into it on Tuesday. All right, thank you so much. You guys know what to do to catch all the basics. I'll see you on Tuesday.